All right. So as I was mentioning, we use this to figure out the distance. The two has to do with the fact that you have to divide the round trip time by two, right? Because the radar signal goes to the moon, bounces back, and bounces and comes back. So if we want to know the distance to the moon, we would divide that round trip time by two. All right. Anyhow, just to let you know, okay. Notice it says here it's not just a radar beam. We can also use lasers. All right. So now a laser, there's a big difference between lasers and radar. They both travel at the speed of light, right? C, the speed of light. Um, that's fine. But what's interesting? What the point of the difference between radar and lasers is radar is a much longer wavelength, right? So it's the form of electromagnetic radiation. It's actually closer to radio than it is to visible light. All right. Now, laser light, of course, is in the visible range, and so the wavelength of laser light is really really small. I mean, extremely small, like you know, um, nanometers in size. Okay, so so now, all right. So occasionally I'll have people who say stuff like, well, we never went to the moon. That it was all a big, it was all staged or something like that. All right. So there, that of course is not true. We definitely visited the moon. And now here's the evidence. Here is some of the evidence of, I mean, nowadays, of course, we can actually see the landing sites, right? The six landing sites on the moon. All right, but that's relatively recently that we've been able to do that with like the Hubble Space Telescope and stuff. At any rate, um, so here's another way of proving that we went to the moon. If you were to shoot a laser beam at the moon, okay, so pick some random location and you shoot a laser beam off the moon. It hits the moon and it just gets absorbed. Okay, I want you to understand that laser light, every time it hits the surface of the moon, would just simply be absorbed. That energy would not bounce back. Okay, ever. It doesn't ever bounce back because of what the moon is made of, right? It's the regolith would just simply absorb that energy. So how is it that we can bounce lasers off the moon, right? I mean, how is that even possible? If you just fire a laser beam at the moon in some random location, that energy is just completely absorbed. And the reason is there are places on the moon, right near where the astronauts landed, where we placed little reflectors. And we know exactly where those reflectors are, right? Exactly where they are. So we know where to aim the lasers, right? And so if we fire the laser at a specific spot, where the astronauts placed the reflectors, then you can get the laser light to bounce back. All right. So that in fact that's exactly why the astronauts put those reflectors on the surface of the moon, is so that we could get a better. What the problem with radar, because it's a larger wavelength, the uncertainty about where what the distance to the moon is, right? When you solve this equation, you don't get a super precise number. Whereas if you use laser light, the time is a little more accurate. Well, not a little bit. It's very much more accurate. Um, because the wavelength is really really tiny. right? And so you can figure out the exact distance to the moon, and in fact, that's how with radar you wouldn't be able to tell, for example, that the moon is slowly moving away from the Earth. It's only with laser light and the precision given to us from lasers bouncing off the moon that we know exactly how far away the moon is, and how fast it's moving away from us. It's not moving away from us very very quickly, mind you. It's that it's taking it'll take a long time for it to move. Even in a noticeable amount, like you know uh, centuries, many centuries. Okay, so it's not anything. All right, so now I mentioned this before that there is, of course, what's called the near side of the moon, the side that faces the Earth, and then there's the far side of the moon, the side that is away from the Earth. And the only way that we can see the far side of the moon is we had to send spacecraft around the moon in the early 1960s to be able to actually see the far side of the moon. All right, and so the reason that the far side of the moon is not visible is because the moon, as it goes around the Earth, it actually spins around its own axis, but it takes one entire rotation around the Earth for the moon to spin around its axis once. So it's it's hard to just. It's sometimes this is the way I generally demonstrate this. Is I'll stand. So it's kind of like Ring Around the Rosie, basically. Like if you ever played that as a kid, I can spin around 360 degrees, but if I do it in such a way that I synchronize the amount of time for me to go all the way around. Like this is what I generally do in the class, right? Is I'll put a podium, the podium, somewhere in the classroom, and the podium represents the Earth, and my face will represent the side of the moon, that that the near side of the moon, right? The side that always faces the Earth. All right. And so what you do is, you start to walk, you walk along, the, in the classroom, you're walking along. And so here's the podium. And, if I like held out a hand in this direction towards the Earth, right? What I do is, I spin 1/4 of the way around, and so I'm still my hand is still facing the podium, or which is represented by the Earth, and then I spin halfway around, and so my hand is still facing the Earth, and then I spin 3/4 of the way around, right, and my hand is still facing the Earth, and then I spin all the way around, right? So I've actually done a complete rotation, but it's taken me one trip around the Earth to do that, and so that's how and by the way, it has to do with the tides. The moon interacts with the Earth, but the Earth interacts with the moon as well, and so this causes the moon to be in synchronous rotation, right? So it's actually in what's called a 1-to-1 resonance. So it takes the moon, for every one time it goes around the Earth, it spins around its axis once, and so that's 1-to-1. There are other moons that we're going to find in the other parts of the solar system where there's a 2-to-1. So they'll spin around on their axis twice for every one time that they go around their host planet. or there's some that are 3-to-1 resonance where that like I said, they'll spin around 3 times for every 1 time that they go around their host planet. All right, so that's what our moon does. It's a 1-to-1 resonance, also known as synchronous rotation. All right, so now the moon, we mentioned this before, but it certainly bears repeating. The moon's axis is tilted by about 5 degrees. Now what is how is it? It's tilted so it's actually tilted 5 degrees with respect to the ecliptic, right? Because when we're talking about the eclipses, right? That's the whole idea of where the ecliptic got its name. Where the moon is with respect to the ecliptic is that's the only time that when the moon is crossing the ecliptic can you get eclipses, either depending on which direction the sun is, but you can have a solar eclipse where the moon is blocking the sunlight, or a lunar eclipse where the moon is in the Earth's shadow. But that's only when the moon crosses the ecliptic, right? And it doesn't do that very often. Now, if you were to compare, so it's 5 degrees. The moon is tilted. When we say the moon is tilted, it's tilted 5 degrees with respect to the ecliptic. Okay, so there's the 5 degrees right here. All right. Now, with respect to the Earth's equator, right, which is also known as the celestial equator, the moon is tilted by about 29 degrees. All right, so if you just compare the orbit of the moon to the Earth's equator, or the celestial equator, it's tilted by 29 degrees. All right, so just to let you know, the reason that we usually concentrate on the 5 degrees is because the ecliptic is where the sun is, and that when it crosses that, when the moon crosses that, there can be if it's new moon or full moon, that's when there are eclipses. All right. So this is going to get into a little bit of the history of the moon, showing you the elevation of the moon. So you can see there's very few regions where there's 8 kilometers in elevation, but there are some regions which are very very deep as well. So this is the average height of the moon, if you will, and then so you have kind of an extreme, like these would be valleys in the moon. These dark blue areas, and the deeper red would be 8 kilometers above the average height of the moon. Is 8 kilometers below. All right, so let's see. Let's see. It's again. It's the moon is very large compared to its host planet, and that's a very unique thing. So what that tells us is that the moon. I mean, this was the first indication when we compared our moon to other moons. The first indication that our moon somehow was very unique. That some perhaps the way it formed was indeed unique. All right, and so we'll get into. So we didn't really know how the moon was formed. There were different ideas around. One was the capture theory, that the moon was just some rogue object and it got captured. Another was the twin formation, the moon and the Earth formed at the same time. Another is the fission theory, that the moon spun out of the Earth, the Earth, and yeah. Anyhow, So these theories were proven different